it's a pleasure, it's an enormous pleasure to have here Osvaldo de Oliveira Jr. It's very hard to say words about him, but he has his background in physics and the master science in physics also in the State University of São Paulo, and his PhD in Wales. And a lot of research contributions, so many papers, so many patents, working in the novel materials, ultra thin films, and many, many things. I would strongly invite you to have a look in his brief comments on his lattice, because it's fantastic contribution, more than 50,000 citations, more than 600 papers, reviewed papers. So it's an enormous pleasure to have you here to talk and use of machine learning, material science, and going beyond. Please, Osvaldo, take the floor, just complete yours, the computer screen and the microphone too. Go on.
Thank you very much, Rubens. I mean, I'm really an honor for me to give this lecture for CINE. I'm also very enthusiastic about the work that you are doing there, you and Flavia and the whole team. And so it's really a pleasure for me to be giving this lecture. So the topic I chose is one in which it's related to artificial intelligence, because it has had so much impact in society as a whole, and obviously in science and technology as well. And because I know there are many young people there who are going to develop the new intelligent systems of the future. So I'm dedicating this lecture to these young guys in the audience. So this is the outline. I'll talk about paradigms through which humans have created and transferred knowledge over history, and then I'll go into specifics of machine learning for various areas, giving examples as well. Around 10 years ago, researchers from Microsoft Research published a book in which they claimed that there are, over history, 4 different paradigms through which humans created knowledge. The first one is starting in ancient Greece was a paradigm or an approach which is empirical, descriptive, because in those times they were not really used to trying to develop mathematical models to explain their observations. This came in the second paradigm with Galileo, Newton, and their followers, in which you have now theory and experiments to generate knowledge. And obviously, this is the main framework of what we do in science technology today. In the 20th century, with the computers, then we learned that we can generate knowledge through theory, experiment, computer simulations. And at the end of last century and beginning of this century, with so much information available in electronic format, we learned that we could gather all this or mine this tremendous amount of data and transform information to knowledge. This is the big data movement. One thing we should notice in these 4 paradigms is that regardless of how expensive, sophisticated the instruments that they use are, or the theories are, at the end of the day, all pieces of knowledge are created by humans with human intervention. A few years ago, I suggested we are approaching an era in which very soon the machines themselves will generate knowledge. This is a completely different paradigm because there will be no need of human intervention. And this will change the landscape of science and technology and of society as well. This, we believe, is going to happen as a convergence of 2 big movements. On the left-hand side, we have the big data movement, through which you use preferably machine-readable contents, because the computers or the machines cannot read yet or interpret text yet. And then you use machine learning for transform information to knowledge. The movement on the right, the complementary movement, is precisely the movement for natural language processing, to try and use data in this case, data from spoken or written text, to transform, to try and teach the machines to read and interpret. And the main reason why we are not there yet is related to these ellipses here. Machine learning is very good. With machine learning, you can do two main types of tasks. Classification tasks, and for this, machine learning is excellent. And this has already been proven, for instance, with facial recognition or with medical diagnosis through images, for radiology images, that provided you have sufficient data to cover your data space, you can do very efficient classification with machine learning, in many cases surpassing the ability of humans. On the other hand, if your task requires interpretation or explanation, machine learning is still not mature enough. So I like to exemplify this difference with a metaphor of the needle in the haystack. For a human, it's very hard to find a needle in the haystack because there is too much stack. You need a lot of processing for doing that. But not for a machine. A machine can do it easily because you can just scan the whole haystack and then find a position in which the materials has different properties from the hay. On the other hand, if you ask the question, how is the hay organized in the haystack? This is a very simple task for a human, but not so for machines, because the machines find it difficult to answer questions such as why, how, what. And when we get there, because it cannot interpret the data, once we can fill in this line here with a solid line in which we have machine learning efficient for explanation, then we'll be there, and then we'll have machines generating knowledge themselves. A lot of requirements are needed. You need a lot of text, and you need ability to analyze text. You need a lot of data from different natures, experimental, theoretical data, simulations, and so on. Things and instruments must be connected so that you can acquire the data. So we need Internet of Things. And obviously, we need to improve our machine learning methods. Today, deep learning with deep neural networks are the most important approach, the winning approach so far, but we will see what the future holds. An example of all of these coming together is in a computer-assisted diagnosis or a fully automated diagnosis system. I'm going to show an example later on. So machine learning is already being used in material science, I would say in two main areas, one of which is materials discovery in different ways. For instance, you can do computer-aided drug design. The whole area of computational biology is now relying on machine learning for making predictions. You can predict synthesis, organic synthesis, for instance. So materials discovery is a very hot topic on machine learning. The other topic is in using machine learning to analyze data from different sources or different types, for image analysis, for classification diagnosis, for Internet of Things as well. I'm going to show one or two examples of these in my presentation. One area in which we are still with very, say, modest results is on knowledge discovery, because knowledge discovery requires that the machines should be able to interpret text. And this is not possible, as I mentioned before, today. Nevertheless, several groups around the world are working on areas for material science in which you can combine machine learning with natural language processing techniques, and therefore you can mine the literature. Because you see, in any given topic that we work on, in any given topic, we may have thousands of papers to analyze, and this is not possible to do manually. So there is a trend now for using these tools, these software tools, in which you can do, say, a semi-automated process, or doing surveys of the literature, or trying to mine information from the literature by combining machine learning with natural language processing. There is a forum on the use of artificial intelligence machine learning for applied materials, which is to be out in the beginning of October. So at any moment, it may be out already. There is a collection in this forum of close to 20 papers on very different types of materials. So there is no limit whatsoever of the area of materials area that you can apply machine learning. But in all of those cases, because machine learning is effective for classification tasks, but not for interpretation. So usually these works involve some types of pattern recognition to classify materials or properties using the databases that are available. And these databases can be made of experimental results or computer simulations or theoretical calculations. And in this very short collection of papers, with less than 20 papers, we already have, in addition to a variety of materials being treated, we have different tasks like prediction of properties. You have prediction of properties of new materials or screening of materials, including for the energy sector, and optimization of conditions for applications. So it's a very diverse type of application that you can have now with machine learning and artificial intelligence. And most of the applications of AI on material science and today, or materials in general, are related with machine learning. There is not much in terms of other applications, other approaches from AI, such as expert system or evolutionary computation, robotics, computer vision. So this is not being used very much for material science, but this is just the beginning. It will probably be used a lot, including knowledge discovery that I showed, that I mentioned some moments ago. There is another arrow in which you can follow. We are used to talking about what machine learning and artificial intelligence can do for material science, but there is the opposite movement. You can use material science for developing the intelligent systems that require hardware, so that all the devices for virtual reality, for Internet of Things, and for robotics, especially soft robotics, they require developments in materials. One area which I like very much is speech processing, because you see, all the speech processing done today in all intelligent systems is done with microphones, high quality microphones, which are deployed in different environments. But now, with all the developments in strain sensors or pressure sensors that are wearable and they can be attached, for instance, to our bodies, and therefore you can capture not only any type of sound or utterances can be captured by these sensors. And in the future, we may have a revolution in this area of speech processing with these devices. Mind you that there will be tremendous ethical problems on this, because you can capture any utterance of a given subject or a given person to whom the sensors are attached. And obviously, a more far-fetched view for the use of material science in AI is to produce machine learning via hardware, because everything that we do in machine learning today is via software in the applications. But there is a tremendous future for using properties of materials and to do machine learning via hardware. One thing which is not mentioned in this slide, but is absolutely crucial, is that most of these wearable devices will need to be self-powered. So the energy, research in energy is crucial for this area as well, for building these artificial systems. So I'm going to show now two examples from our own group and collaborators in which machine learning is used to analyze sensing data. The first example is a genosensor to detect the virus, the SARS-CoV-2, actually to detect a DNA sequence which mimics the RNA of the virus. So we produce the genosensor, and then we deposit this genosensor, or the produced genosensor on this interdigitated electrodes, and then we could detect the sequence of the DNA sequence with either spin density spectroscopy, electrochemical spin density spectroscopy, through optical means, but we could also do optical image analysis, because the idea we have in the future is that we have a sensor, a biosensor, we expose to the sample, and then we take a picture of the sensor before and after, and then we do image processing to do the diagnosis without having to use any instrument. So as a proof of principle, we use low resolution scanning electron microscopy, which is equivalent to optical microscopy. And in fact, it does work with optical microscopy. And so we took pictures of the sensors without with a blank sample, which means just a buffer without the sequence, the DNA sequence, and then negative controls, which would be genetic material from negative sequence, not as a sequence which is complementary to the one we are, to the probe we had. And then we had genetic materials from other cancer biomarkers, which are not related to COVID-19. And then the different sequence concentrations of our DNA sequence. Visually, you see that as you increase the concentration, your sample is, the sample is more, or the electrodes are dirtier, but you cannot infer any information whatsoever just with visual inspection. On the other hand, if you do image analysis and you apply supervised machine learning, you can get almost 100% accuracy in saying yes or no for the SARS-CoV-2. And if you want to distinguish between the different concentrations, and then you can still do multi-class classification, and you still have close to 96% of accuracy. Now I'm going to show a concept which we put forward this year, which is called multidimensional calibration space. It's an analogy to the calibration curves in analytical chemistry. So in calibration curves in analytical chemistry, you have normally just one variable, normally concentration. Then you have a high accuracy within experimental error. So if you have a very good a calibration curve, so you don't make mistakes. It's limited to the linear region, or as defined by an equation. And obviously, you can only classify samples of the same class. So if you have, say, data from an electronic tank for different wines, you cannot have a calibration curve. So we created this concept of calibration space because you can remove these limitations. You can treat data from electronic tanks, noses, or do diagnostics in general. So you can treat several variables at once, and you can have the ability to distinguish and predict classes. I mean, it's similar to what people do in chemometrics or multivariate analysis, but here we establish rules which can actually distinguish the different and predict the classes. So we replace a calibration curve by this multidimensional space. Rather than have equations, we have rules from decision trees or random forests, which are two machine learning algorithms. And then the number of dimensions of our space is the number of features that you have to use. Like, for instance, if you have 2 or 3 frequencies in a capacitance spectra, then if you use 3 features, you have a 3-dimensional calibration space. The number of rules that you need is the minimum is the number of classes. And then you can also apply concepts like row coverage and feature importance for your space. So I'm going to show one real examples of a sensor which was bad. This is a sensor for phytic acid, which was not specific. So we measured different concentrations of phytic acid, but we could never distinguish the different concentrations, especially some ones. Even if you applied, principal component analysis or these other statistical methods. But using our concept of multidimensional calibration space, we could find a space which is a 3-dimensional. So you have a matrix with 3 dimensions. These 3 dimensions are different frequencies, are represented by different frequencies. So we needed to measure the capacitance at 3 different frequencies. And as you combine this data with rules, we could establish a space, because it's three-dimensional, could represent, use this alternative representation, so that every time we have a new sample, we go to this calibration space, and then we can see, for instance, in this maroon, this brown region here, we know this is the sample 10 to minus 5. This one, the green one, this greenish color here, is a more difficult one to classify, because you see, you have different entrances here for this classification. So with this method, we can classify any type of data. I use here for sensing data, but this can be used for text. You can combine data from clinical exams, with images or so on and so forth. There is no limit to the sort of data that you can use. And you can explain, you have a calibration space, because you can have rules to explain how you classify the samples. Now comes with all these type of technologies. If you combine the different technologies, we can have this Holy Grail in which we have a system to assist doctors or to do automated diagnosis processes by combining not only the data from one patient, and this data can be of a multi-nature data. So you can have text, you can have data from sensors and biosensors, you can have data from images. But then, rather than using the data of a single patient, as we have now the medical doctors doing, we can have a repository of hundreds, thousands, millions of patients. And then you do all those processing and pre-processing that are required. And at the end of the day, you use methods from machine learning to do classification, to do regression, and then you have the diagnosis. We are bound to have much better diagnosis using these systems. But obviously, this is only possible if you have these conversions of the two types of technologies. In science, obviously, you need a lot of computational power, you need machine learning, as I have mentioned, but obviously, we need quality data. We need to understand this sort of data we are collecting to try and train our intelligent systems. And therefore, these words here are important for sensing and biosensing, for other types of technologies related to diagnosis. And then we need to understand this as well. So we can only get there by combining these two types of technologies. I'll be finishing by making a statement that in a few years or in a few decades, most of the intellectual tasks will be better performed by machines than by humans. We need to prepare our society for that. And then, and this is for the young scientists, that whenever you're doing a project, you may ask yourself how an intelligent machine would solve the very same problem. Because machines are entirely different from us. They have almost unlimited memory compared to ours, tremendous processing capability, much better, much higher than we can do. And perhaps the machines can solve problems in different ways. And it's always important to ask ourselves this question. And I have a long list of collaborators involved in this work that I showed, and I thank you for your attention.
Thanks very much, Osvaldo, for very exciting, very interesting talk. And let us to be happy and worried at the same time, but it's quite interesting. Please, the floor is open for the questions. I understand that there is one hand left here. Marco Antonio, maybe you can make the question, is that right? I have one question, Osvaldo. Yeah. How can you, how far we are from the interpretation of text, the first things that we have to do, and how can we deal with, for instance, fake, let's say, not fake news, but when report work is not good enough to be considered. do you think that is that possible to have some kind of a way to judgment to evaluate the value of that information to be accounted for?
Yeah, that's a very good question. So let me answer the last part of it. Detecting fake news is not that difficult because you do not require a lot of language processing for that. You know, if you, for instance, if you track this source of the news, of the piece of news, by tracking the source, you already can do a lot in terms of detecting fake news, because in many cases, some sources, they only spread fake news. So this can be done, and I think there are groups working on that, including in São Carlos, our nucleus for computational linguistics has been working on this and on detecting fake news. And in fact, detecting a fake news, they have a very high accuracy in saying that the fake news is really fake news. It's a little bit more tricky to, when it's not fake news, then the accuracy in the classification is not as high. But for detecting fake news, they can get more than 90% accuracy, and you'll be able. And it doesn't really require a lot of language processing. Language processing, natural language processing, is the biggest challenge we have in artificial intelligence now. There is no other challenge that's more important than this, because you can imagine all the assistants we have around us, all the systems that are being developed. If any of these systems could interpret text, our life would be entirely different. My guess is that it will take perhaps 10 or 15 years more, but it will not come at once, because researchers are finding ways to sort of divide the interpretation tasks into classification tasks. As long as you can do that, then you can perform well. You see, with machine translation, for instance, we already have very good systems for machine translation, which was deemed impossible only 10 years ago. So 10 years ago, people would never have believed that we would have machine translation system as efficient as the present ones. And this has been possible because you can actually split an interpretation task into, say, classification tasks. It will come, it will not be easy, but I might guess that perhaps in 10 or 15 or 20 years we'll have it. And this will change everything. That's why I find it so important to be talking to the young people in the audience.
Right, good. Thanks very much, Osvaldo. We have one question from Luis Felipe Leoneto. If you don't mind, I will read it to you. Are there any disadvantages of using machine learning for materials development?
Disadvantages?
Yes.
No, I think there are limitations. The limitations are essentially based on the fact that because machine learning is very good for classification, but not for interpretation. So you need to have, in addition to very good quality data, you need to have a very specific question to be answered. So you need to know what you are looking for. Otherwise, machine learning is not useful. So this, I would say, is the most important limitation. As for disadvantages, I would say that if you don't use it properly, you get the wrong answers. So you may be fooled by the answers that the machine learning system provides. And this can be either because the data was not sufficient to cover the data space that you are searching, or because the questions you are asking are not the adequate questions. But where I see the disadvantage of the intensive use of machine learning is for societies as a whole, because as a very knowledge-intensive technology, it brings inequality. I mean, it's bringing, as you know, as we see now, the most developed societies, the richest societies, are very intensive in technology, in knowledge creation, knowledge generation, and obviously this is going to bring more and more inequality among people in a country, among people in the same country, and obviously among nations. And therefore, if you do not have a lot of investment in education and in science and technology, these new tools will bring more and more inequality for our people in Brazil. So that's something which worries me. But I would say it's inescapable. We cannot
Yes,
avoid
it's a
it.
challenge. It's a challenge that we have to overcome. Yeah, very good. Uh, let's see. I think we have one more question. It's quite long one, but I read to you. Congratulations, Shu, for very nice presentation. More important for addressing these very new critical points in the pioneering manner. My questions regards to the reliability of the characterization data. How is your perception about the current intelligence artificial and the machine learning capacity to do this comparison in an automated manner? For instance, to find the actual selectivity capacity of a sensor family. Generally, test mining is limited to manage number and units. So how can you implement this in a practical manner? That's the final question.
Well, that's a very good question. Thank you for the comment.
Holy Ribeiro de Oliveira is the author
okay,
of
thank you, guys. I mean, the main limitation I see for sensors and biosensors, and for other areas as well. I mean, for instance, in the energy sector, I think we lack solid databases which are sufficiently comprehensive, quality data, and well organized. So the most important thing which is lacking today is data, quality data. For instance, for sensors and biosensors, we do not have any, as far as I know, we do not have any international multi-institutional initiative to have, a big database of sensors for sensors and biosensors. So we need to have that in place, and then we'll be able to use machine learning effectively. So far, we've been using machine learning not for big data in sensing biosensing, because we do not have big data yet. We use only for small data sets, and this is limited. But once you have large data sets, as we have, for instance, for the protein data bank, or for image analysis for cancer, for instance, we have tremendously big and accurate image analysis, image databases for cancer or in other diseases. So once you have that for sensors, then we can apply machine learning, and probably I'm really confident the results will be fantastic, because it really works. It's working with small data sets, and for big data sets, that's for sure it's going to be even better.
Very good. I have one more question, if you don't mind, Osvaldo. It's quite exciting topic. We know that the artificial intelligence is just a fitting some of the neural networks, for example. We are fitting data, in fact. What's your vision about the maturity of this machine learning to be able to gain with experience? Do you think that machine is going to be able to gain with experience in learning?
Yes, it will. Yeah, it will learn a lot, and it's learning quite efficiently in many ways. In natural language processing, for instance, you may have seen in the press text generated by machines, which is absolutely incredible. I mean, it's incredible to see the texts that are generated with the machines. And they are generated with such efficiency because the machine learned or were trained with a tremendous amount of data. If you take everything that has been ever written, and it's in all books, in all places in the world, in all libraries in the world, even if you take all, it is still less than the amount of text that they use to train some of these systems. For instance, for English, they use the Wikipedia database for training, and they talk about a database with more than 5 billion words. So the machines will learn very effectively once you have a lot of data and the data has good quality. But as to move from this classification to interpretation, which is the big challenge, I would say that there are two different ways. One is that we need to find you need to find ways to transform interpretation questions into classification questions. So we need to do it somehow. So that there will be this we need human intelligence. The machines cannot do it yet. That's one thing. The second one is that you have to start learning how to ask questions to the computers so that the computers can do, or the intelligent systems can do more sophisticated things. For instance, you may give a lot of data to the computers and show models to the computer and to the system and try to match, so that the intelligent system will start producing models to explain data, and it will learn to do it. So really, I mean, it's a very exciting field. There is a lot going on, and it will go on and it will progress at a fast pace because of the economical value. Because the companies are making tremendous amount of money, as you know, even in cases that we do not wish, but they are making a lot of money with artificial intelligence. And the only thing we can do is try and jump on the wagon and try to do AI with responsibility, with ethics, and try to develop things for our own people. For instance, one thing which bothers me a lot is that I want to develop tools for Portuguese before we have to import all the tools produced by other nations. Because you see, one of the key areas now in machine learning is called transfer learning, in which you use a data set of a particular application, then you can train your intelligent systems with this data set and then apply to another data set. And the data sets can be in different languages. And therefore, you can train some tools to do language analysis or language generation in a language and then transfer the knowledge to another language. So in a few years' time, unless we do it for Portuguese, these systems, intelligent systems, will be made by the top guys or the top companies in the world, probably from China or from the US. So we have a window of opportunity that we should take now.
Very good. Osvaldo, it was fantastic talk.
Thank you.
The subject is, let's say, very exciting. We could stay all day discussing. Your answer for the questions were also very, very clarifying. Your point of view is quite interesting for the country, especially for a developing country. That you are right, in my opinion. We have to take care of this. Knowledge is essential. And I'm not so young, but I'm very interested in pursue machine learning, to learn more things, because you have this thirst to learn, and that's quite interesting. I would like to thank you very much. It's a really pleasure to have you here. You are a standout outline scientist. And then I'm very, very happy to have you here in your section this first day. And I'm sure that this more than 200 people are very, very curious to know how they can learn more using the computers to help them to learn. That's the point. Thanks very much, Osvaldo. It was a pleasure to be with you.
Thank you. And have a nice conference workshop for everyone. Thank you very much.
Thank you. So we are approaching the closing of this first section. And then section 2, this first day is going to happen 2 o'clock in Brazilian time. I can see that people from abroad are just watching us and be with us. And I'd like to see if Juarez or Ana Flávia wants to talk something, or can end this section. Ana Flávia.
Oi, Rubens. I think we can close the session. See you at 2 p.m. Thank you, Shu, for this very nice, amazing talk.
Okay.
Thank you.
So thanks very much, Shu, again. And thanks very much to everybody, to all the support team that helped us to be here up to now.